Before we do some examples, let's take another look at confidence intervals and hypothesis testing for the difference in population variances. Okay, first off, let's recap the F distribution. Okay, this was a new distribution that we learned in this chapter, or in this unit. And for the F distribution, it has two different parameters. Okay, two different degrees of freedom. Let's call this degrees of freedom 1, degrees of freedom 2. Okay, has a shape that kind of looks like this. And if we want to find, let's also talk about this. So, because it has two different parameters, degrees of freedom 1, degrees of freedom 2, we're very limited on the number of values on the axis that we can get in a table, right? Because we have to have a different table for every tail probability, okay, for two different degrees of freedom. Okay, so this makes it a lot more difficult to publish a table of these things. Okay, that's my point there. So what we have is an upper tail probability that's given by a particular table. So we'll have a table, for example, for 0.1 in the upper tail. Okay, we have degrees of freedom numerator, degrees of freedom 1 running across the top, degrees of freedom 2, degrees of freedom denominator running down the rows. Okay, so the intersection of that column and row of our interest for 0.1 in the upper tail will give us this value. Okay, and we have a different table for different upper tail values, 0.05, 0.025, 0.01, and so on. Okay, if we're not using Excel, that is, we're just using the tables that were provided in any kind of textbook or what were provided in this course, that's how you would read a value on the axis associated with that amount of area in the tail. Okay, so if we want, let's say, this area down here, and let's just call it alpha over 2. Okay, let's call this alpha over 2, just in general. Okay, so if we want this value down here, and let's just refer to this as f of degrees of freedom 1, degrees of freedom 2 for alpha over 2 in the upper tail. Okay, let's say we want this value down here as well. Okay, so we kind of have to think back to the chi-square distribution. And the chi-square distribution said that up here is the upper tail. Okay, up here is the upper tail. So if we want alpha over 2 down here, we want 1 minus alpha over 2 in the upper tail. Okay, so this value on this axis would be for degrees of freedom 1, degrees of freedom 2, and 1 minus alpha over 2 in the upper tail. Okay, so up here we're fine. We've just got alpha over 2 in the upper tail. Down here, if we want alpha over 2 in the lower tail, then we need to find the complement of that in the upper tail, 1 minus alpha over 2. For the chi-square distribution, we had different columns associated with, 0.1 and 0.9, 0.05 and 0.95. Okay, so it gave us several different options for values in the upper tail, whether they be small or large. Okay, but here we have a functional relationship between this value and this value. Okay, and what that is this. This thing is equal to 1 over an f value. If we switch the degrees of freedom 2 comes first, then degrees of freedom 1, alpha over 2. Okay, this thing right here, okay, with 1 minus alpha over 2 in the upper tail is equal to 1 over f with the degrees of freedom switched, alpha over 2 in the upper tail. Okay, so that's a nice property because we don't have to have different columns for 0.05 and 0.95 in the upper tail. Okay, we can just still use this, but we have to switch the degrees of freedom. That's a very important part. We've got to switch the degrees of freedom. Okay, so for hypothesis testing, what we're doing here with an F distribution is we are comparing the variances of two different populations. Okay, we want to know, for example, is sigma 1 squared equal to sigma 2 squared? Okay? Or is sigma 1 squared not equal to sigma 2 squared? Okay? That's what we want to know. Are these two variances equal to each other? The variance of population 1, the variance of population 2, are those two equal to each other, or are they not? Is the variance for population 1 greater than or equal to the variance for population 2, or is it less than? Is it less than or equal to, or is it greater than? Okay, so we have three different options, just as always, for comparing these variances for these two different populations. Okay, and the way we answer this is with an F test statistic, which is S1 squared over S2 squared. Okay, so the idea here is if S1, for example, is a lot bigger than S2, okay, if this variability of population 1 is a lot bigger, it's a lot more dispersed than population 2, then this ratio is going to be a lot bigger than 1. Okay? If this is smaller than this, it's going to be less than 1, or maybe a lot less than 1. Okay? So we're really going to be comparing how big is this ratio. If it's really big, it's going to lie out here. If it's really small, it's going to lie down here. Okay? And so we could easily do the critical value approach, right? So if we have equal to, not equal to, that's a two-tailed test. We could find this. We could find this using this property. We've got two rejection regions, and we could determine if our F statistic lies in the rejection regions or not. Okay? If we have a one-tailed test in the lower tail, we've got right here. Okay? We've got this property. We can easily find what this critical value would be. Upper tail, same kind of thing. Okay? We could just calculate what this critical value is associated with alpha in the upper tail for this circumstance, and compare our test statistic up there. Okay? Calculating p-values, not as easy with just the book. Okay? We would have to use Excel to calculate p-values for this kind of situation. So this is hypothesis testing. Now let's talk about confidence intervals. Okay? For a confidence interval, we are creating a confidence interval for this ratio. Okay? That's the best we can do. Okay? What's the confidence interval for the ratio of sigma 1 squared to sigma 2 squared? Okay? And that is a function of the ratio of S1 squared to S2 squared. But up here, this F statistic, or this F value, the value on the F axis, note here, this is an important distinction. We are counterintuitively reversing the degrees of freedom. Okay, I should note here that for our purposes, degrees of freedom 1 is equal to n1 minus 1. Degrees of freedom 2 is equal to n2 minus 1. Okay, so we have to reverse the degrees of freedom. Degrees of freedom 2, comma, degrees of freedom 1. Okay, it's an important distinction for alpha over 2 in the tail, in the upper tail. Okay, this is the bigger number, so it would be up here. Down here, we've got the smaller number. Okay, F, degrees of freedom 2, degrees of freedom 1, for 1 minus alpha over 2 in the upper tail. Okay, that's the smaller number. It's going to be in the lower bound. And we multiply that by S1 squared over S2 squared. Okay, how do we find this? Using the table in the back of the book, or in the tables that are provided, we've got this property. Okay, so we could easily find this. That would be F n2 minus 1, comma, n1 minus 1 for 1 minus alpha over 2 in the upper tail. That's equal to 1 over, flip the degrees of freedom, F, n1 minus 1, n2 minus 1 for alpha over 2 in the upper tail. Okay, we could plug that in right there, and then we could calculate out our confidence interval for the ratio of variances from population 1 to population 2. Okay, so we've got statistical inferences for the differences in population variances. We've got hypothesis testing, we've got confidence intervals, and we've introduced now in this unit the F distribution to help us with all of this.